going to start the first session of the advanced track. You're going to have a host of speakers today. First one being Dr. Daniel Sank of quantum AI. We're going to talk a little bit about leakage and superconducting qubits. After this, we'll have a second talk by Oprah. Oh, you just left? Okay. And after that, there will be lunch. Lunch will be served outside of this room because you can't be in this room for lunch. And then we'll follow up in the afternoon with some further talks from Michel Devoré, Andreas Marab, and Vlad. Without further ado, I hope everybody online can hear us. I'm anyways going to be there. Let's get started.
Yeah, let's see. Somebody online, let me know if the mic works.
Mic works perfect.
Great. Okay. Right. So my name is Daniel Sank, and I'm currently at Google. I did my PhD at University of California, Santa Barbara with John Martinez, working on superconducting qubits. And I got bitten by the bug, and I've been doing that ever since. So that's what I'm going to talk about today. In particular, I'm going to talk about leakage. Now, why did the title of my talk change from what's on the schedule? So this is supposed to be a design workshop. Why am I talking about leakage? So as I was making my original presentation about actually how we design our devices, I realized that a lot of the constraints that go into how we choose what device to make in the first place come from handling leakage. So I figured maybe I should just talk about that. The literature has a lot of examples of qubit reset and leakage removal methods. There's also many papers about making readout faster and faster, but I've seen few to no papers that talk about doing both of these things at the same time in the same device. And so one of the main themes of this talk is going to be to explain to you, I think, why that is, why that's so rare. Essentially, it's because it's difficult. So my main goal in this presentation is to convince you that when you think about designing your device, you really do need to take both of these things into consideration and then use all the methods that you'll learn in the rest of the workshop to bear on solving that problem. Okay, so here's an outline of the talk. I will briefly review how the surface code works and then comment on why leakage is such a problem in the surface code and in other quantum error correction methods. Then I'll talk about how qubit reset and leakage removal actually work. Then I'll talk about leakage that comes from the readout process itself. And at the end, just in one slide, I'll bring it all together and try to explain what the implications are for the device architecture or in the designs that you might be making yourself. So let's start with the surface code and why leakage is bad. Okay, the surface code is meant to solve the problem that we're trying to do quantum computations, but individual qubits don't live for very long. So we put a lot of qubits together in a big grid and treat them like one logical qubit. So how does that actually work? So the basic idea is you make a grid of qubits as shown here. Half of those qubits store the data. Those are the white ones, the little white circles. And the other half of the qubits we call measure qubits. And their job is to measure certain properties of the data qubits. Those are the ones shown in black circles. There are two flavors of measure qubits. There's measure X and measure Z. So the yellow crosses, that's indicating that that measure qubit at the center of the cross measures the four-way XXXX operator on the qubits that it touches. And similarly for the measure qubit in the green cross, it measures the four-way ZZZZ operator of the qubits that it touches. Now, you know in quantum mechanics that non-commuting operators can't be measured simultaneously without scrambling the state. So what's going on here? Well, it turns out that XX and ZZ actually commute. So if you have two measure qubits as shown here in the zoom in that are both touching data qubits 1 and 2, actually you can measure XX and ZZ on those two qubits and they're compatible and you'll get a state and that state will not change after you measure those parities. So it's not like measuring X and then Z and then X and then Z on a Bloch sphere where you recollapse the state every time. Turns out actually the eigenstates of that are Bell states. But you can't do quantum error correction with just two qubits. It turns out you actually need more, and I have some backup slides explaining that if anyone's interested later. But the point is that if we measure all of these four-way parities, they're all commuting with each other. So this grid of qubits will fall into some eigenstate. We don't know which one a priori, but it will fall into a stable state. Okay, and it turns out, I should mention that once you've measured all of those four-way operators, and on the edges there's some three-ways, but that's okay, you wind up with 1 degree of freedom left over in this grid of qubits. And you can tell that actually because if you count the number of data qubits, there's one more than the number of measured qubits. So even after measuring all these parities, there's 1 qubit's worth of information that you haven't measured yet, and that's the logical qubit that you're preserving. All right. So what happens if a physical qubit actually suffers an error? So for example, let's say that one data qubit that's got a little red X on it suffers an X error. What will happen is that the parity measured by its neighboring X measured qubits will change on the next round of operations. So you can uniquely tell if those two red cross measure qubits change their parity. You can uniquely tell that the qubit in the middle must be the one that had an error. And that's good because you know exactly where the error was, and you can either fix it or just take it into account for the rest of the computation, and everything's fine. And that is basically the essence of quantum error correction in the surface code. Similarly, if you have a low density of multiple errors, so here we have 2 errors, 2 qubits that have an X error, what will happen is that the X measure qubits on the ends will see a parity flip, but that one on the bottom left there won't, because it's touching both of the qubits that had an error. So that's 2 parity flips, which is no parity flip. So what happens is when you get little chains of errors, you get a detection event on the endpoints. And that's how, as you go through the surface code, you can tell what happened, at least with some sufficiently high statistical significance. Now, the thing that can happen that can mess you up is if you get a chain of errors that crosses the grid. If that happens, you can see that every single one of the X measure qubits is touching an even number of errors, so it doesn't see a parity change. That would be a logical error. That's also how, in a sense, it's not really how you do it in practice, but that's also, if you want, the operator that you need to apply to get the logical qubit state to change if you actually want it to change. So you would just essentially apply a chain of X operators across the grid like that. That's not how you do it in practice. There's better ways of doing it, but heuristically close enough. The whole story also runs for the other direction. If you go horizontally across the grid and you do Z errors, that's how you change the Z state of the logical qubit. All right, so that's the basic idea of the surface code. Now, I've shown you everything in this 2D grid, but there's also time. So you're doing these measurements sort of stroboscopically, boom, 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 in time. And so you can also have chains of errors or just errors that go in the time direction. And at the end of the day, what you wind up with is a cube, 2 space dimensions and 1 time dimension. Imagine just a box, and it's full of errors. It's like little stars in the sky in this box of errors. And in order to actually run a quantum computation, you have a classical computer that's that we call the decoder. And its job is to take all these errors that are happening and figure out what happened with high enough accuracy that at the end of the day, your quantum computation can be done without any logical errors. Okay, so that's what a decoder is doing. So why is leakage such a problem? So leakage increases the rate of errors popping up in this 3D volume. We call each one of these detection events, well, we have detection probability. So that's like the statistical distribution that you're going to have a detection event somewhere in this volume. And on this plot on the bottom left, I'm showing you the detection probability as a function of cycles of the surface code. And you can see how it's gradually going up over time. That's happening because of leakage. And this is a problem because if your error rate is getting worse and worse and worse as you run your computer, eventually the whole thing's going to fall apart. Okay, you have to attack this head on. There have been some experiments where the authors were able to detect when leakage happened and just discarded those trials from the data that they're reporting. That's actually a great idea if you're trying to focus on some other demonstration where you don't care about leakage. If you're actually trying to do a computation, you can't throw trials out, especially if they're happening too frequently, because you never get to finish. We have to solve the problem. Well, why didn't that work? Okay, let's see if I can advance my... Okay. All right, so why is leakage more problematic than any other kind of error? This is important to understand. So here, what I've drawn is a quantum circuit representation of that same surface code that I showed you before. So now instead of showing the physical patch of qubits, each line represents a qubit. We have the data qubits and the measure qubits. We have the C0 gates between data and measure qubits. Those are how the measure qubits pick up the parity of its neighbors. And so what we have is each measure qubit does some C0s and then gets measured, and then does more C0s and gets measured, and that's the memory cycle through the surface. So normally, if you didn't have leakage, you might have some, bit flip errors on a single qubit. You could have errors in the measurement, But those are exactly the things that the service code is designed to handle. Now, take a look at the little transmon cartoon on the left. Leakage is when you hop from the one state, let's say, to the two state or any other state. It's actually funny. I should have defined leakage. By the way, leakage means going to a state that's not the 0 or 1 state. Should have said that at the beginning. Okay, so what happens if this data qubit at the bottom leaks to the two state in the spot shown there with the pink L? A few things can happen. First of all, that two state might live for quite a while, especially as qubits get better and better and their T1s go up, that leakage will survive longer and longer. So actually leakage becomes more of a problem as your qubits get better. So it's going to sit around. And every time that qubit tries to do a CZ gate with its neighbor, if it's in the two state, the gate's not going to do what you wanted. So the gate's going to have an error. But what's even worse is that because of the way the gate actually works physically between the two qubits, that leakage can actually move to its neighboring qubit. So you might wind up putting that neighboring measure qubit in the two state instead. And then that could screw up the measurement result. And then that two state might transport to another qubit. And so now you've got these errors that are spreading around the surface code and they're correlated. And that's something that the decoders are not good at handling. You can do a really good job with decoders if you're able to assume that the errors are not correlated with each other. But as soon as they are correlated, your probability of accurately understanding where the errors happened and what's going on drops very quickly. This is why leakage is such a problem. It spreads all over the place and it confuses the decoder. Yeah, go ahead.
Is leakage something that happens unexpectedly, or is it something measurement?
Yeah.
I don't see measurement and leakage.
Yeah, that's a great question. So the question was, does leakage happen in some expected situation? Does it happen from the measurement? I think you're just asking what causes it. So as I alluded to at the beginning, leakage absolutely can happen due to the measurement, and I'm going to talk about that in detail later. It can also happen because the qubits are not at 0 temperature. So you can compute the Boltzmann probability of being in the two state. It's not 0. Typically, I would say that, in my opinion, most transmons are probably not in thermal equilibrium with a temperature that makes any sense. There are noise sources that are hard to account for, and those also kick the qubit up into the two state. Moreover, one of the popular ways of doing a control NOT gate with transmons actually involves temporarily occupying the two state. So if you don't get all the probability out of the two state, then you've got leakage. It should also be said that transmons do not have a particularly large anharmonicity. So the difference in the transition frequency from 0 to 1 and 1 to 2, typically a few hundred megahertz. It's not enormous. And you can't make it bigger because if you try to make it much bigger, you get charge noise sensitivity. And I want everyone in this room to be upset by that statement. We have been bullied by charge noise in this field for too long. And if you're looking for something impactful to do in your PhD or your postdoc or in industry, figure out where the charge noise is coming from and get rid of it, or figure out a way to make qubits that aren't so sensitive to it. That would change the design problem in fundamental ways that we don't even normally think about. So I hope that inspires at least someone in here. Okay. All right, so how do we handle this problem? Let's talk about reset and leakage removal. Well, can we just remove it somehow? So suppose we had a leakage. Let's look at the top example there. We had a leakage on a measure qubit. So it leaks, we measure it. Maybe the measurement is wrong because of the leakage. So the measurement is in a red box. That means there was an error. Can we just do something to get rid of the leakage and then move on with our lives? That might actually not be so hard because once you've measured a qubit, you've collapsed its wave function and you're not trying to preserve any nice quantum information. So you could do something kind of brutal there. But what happens if the data qubit leaks? So that one we're not measuring. That has to stay in a nice quantum state. So is there any way that we could get rid of leakage in the data qubits, but leave the 0-1 subspace alone? And that would be the double question mark, right? That we may need to do that. So first, let's do the easy one and then the hard one. All right, so this diagram in the top left shows how we do what we call multi-level reset, or MLR. This is a gate that resets the qubit to the ground state, whether it's in the 1 state or leaked into the 2 state. So here you have a plot of the qubit's frequency as a function of time. And you see there that there's this dashed orange line that says resonator frequency. So we have a lossy resonator at a frequency that's lower than the transmon. And when we want to do reset, we simply tune the qubits frequency down and cross the resonator. Now, why does that work? Let's look at this level diagram in the bottom left. Oh, is everything getting cut off because the slides are, oh, geez. Okay. Yeah, let me see if I can do that. Sorry, AV issues, hold on. All right, let's just do it that way. Can I what? If you want to try, oh, did that work? Oh, great, okay. All right. So here's the nice thing about the transmon. Its anharmonicity is negative. So as you move the transmon down in frequency, the 1 to 2 transition crosses the resonator first. Then as you keep tuning the qubit down, the 0 to 1 transition will come onto resonance afterwards. So if the qubit was in the 2 state, the first thing that happens is you transfer the 1 photon into the resonator and the qubit's in 1. Then as you move it farther down and the 0-1 transition comes on resonance with the resonator, you transfer another photon to the resonator and you go from the 1 state to the ground state. So by pushing all those higher levels through the lossy resonator in order from highest to lowest, you get this multi-level reset. And it's great. It's the greatest thing ever. It works incredibly well, as you can see here. So this is a plot of, sorry, you know, my PhD advisor had a fortune cookie label on his office door that said, digital systems are made of analog parts. And I'm thinking of that right now because I'm using a scroll wheel to go through my slide. You have to tell a joke there. Okay. So here we measure the 2-state population as a function of the repetition code cycles. And we have one case where we don't do MLR and one case where we do. So this is for a measure qubit. And you see that without MLR, the population in the 2-state is going crazy. It's going up to like 1.2% after 30 rounds, which is catastrophically bad. If you turn on MLR, it's close to 0. So that's great. Now, another thing that happens though, and this is kind of a bonus that you might expect if you thought about it, is that the data qubits also get better. So the measure qubits are squares and the data qubits are circles. And you see that the data qubit 2-state probability also goes down just by resetting the measure qubits. And the reason for that is what I mentioned before, that the leakage can transport through the 2-qubit gates. So as long as you have a sink somewhere in the circuit, you're pulling 2-state out and it helps both kinds of qubits, which is nice. Okay, now that was the easy one, was getting rid of leakage in the measure qubits, but what about the data qubits? Okay, so we have this delicate data qubit. We already know how to measure and reset the measure qubit. So let's see if we can cook something up to directly remove the 2-state from the data qubits. So here's what we do. You just stick basically a swap between the data and measure qubits after you've resetted the measure qubit. But that swap is tuned up to only swap on the data qubit the 1 to 2 transition. So you're swapping 2-state from the data qubit into the measure qubit, and then we reset the measure qubit again. So this MLR reset, this reset thing that we use on the measure qubits is coming into play yet again. So the idea here is basically like this. If the data qubit leaked, you're going to swap it into the measure qubit and then reset it. And so that cuts off any further error in the measure qubit. And the only thing that's happened to the data qubit is that it's back into the 0-1 subspace. So at worst, it suffered a poly error, which is tolerable. The service code can handle that. Okay, so that's we call this data qubit leakage removal, or DQLR, and that's how the operation works. Okay, so let's do some simulations and see what we think is going to happen. Now, as you're looking at the next few slides, you're looking at the next few slides, notice that the top half is in a linear scale and the bottom half is in a log scale, because when we start removing leakage, the leakage probabilities are going to drop really fast. Okay, so with no reset, the data and measure qubits leak, and it's all horrible. That's the red color. Now we turn on the multi-level reset, or MLR, on just the measure qubits. This is what I showed before, and they both get better. The measure qubits get a lot better. They're, a few parts in 10 to the minus 4 leaked, which is okay. And the data qubits got better, but they didn't get better enough. So let's turn on this data qubit leakage removal and see what happens. So now we're in the blue, where we're doing both things. And you see that the measure qubits have gone down below 10 to the minus 4 basically into a regime where our error bars are enormous and we can't really measure anything. But the data qubits also now have a very low probability, about 10 to the minus 3, of being leaked at any point in the service code. And that's low enough that the decoders can handle. So this DQLR seems like it should work really, really well. And then indeed, in one of our more recent papers, we found that, yeah, it's great. So this is from the Nature paper that it was on arXiv last year, but it finally showed up this year, 2025, where we did quantum error correction below the fault tolerant threshold. So we showed that the logical error rate is actually getting better as we add qubits, which is a good place to be. And data qubit leakage removal was an absolutely essential part of that. So let's look at the top left panel. So here we're plotting the logical error probability as a function of error correction cycles for a distance 3. So that's where that surface code patch is a 3 by 3. And for distance 5. So the patch is 5 by 5 data qubits. So let's take a look at the distance 3 first. That's the red. So there you can see that the logical error probability doesn't change really much at all when we add DQLR. It gets a little bit lower, but not much. However, when we go to distance 5, you can see a pretty big difference. And that's something that we actually expected, and something that I think a lot of the field is going to have to face pretty soon. When you have small experiments, it turns out that the impact of leakage isn't that bad. But as you get past distance like 5 to 7, that's when leakage really starts to matter for decoders. So if you're trying to do any real quantum memory experiment, you really have to face this leakage problem. But it's great that here we can see that it really made a pretty big difference in the logical error rate. Somebody wanted to ask a question a minute ago, and I kept talking. I answered your question. Excellent. Okay.
So can you elaborate on this, why it becomes more important?
Okay, so the question was, can I elaborate on why leakage is a bigger problem when you have more qubits? The honest answer is that I probably don't understand decoders well enough to answer that question. If we could, let's maybe chat after the talk. I'll think about it a little more. Yeah.
Yeah. So for the MLR, you said you use a resonator. Is that the readout resonator of the?
I'm going to come back to that. The question was, when I talked about MLR, I said that there was a lossy resonator for the reset. And the question is that the same resonator that we used for readout? I'm going to talk about that later. That's the punchline of the whole talk in a sense. Okay, great. And I also wanted to point out that this logical error rate is pretty stable over time. And that's very good because among other things, it means that that very careful swap we tuned up to swap the 2 state out of the data qubits, that kept working for 15 hours or so, which is good and something you might worry about. If you do something wrong in this data qubit leakage removal process, for example, let me go back because I really should have emphasized this. If this reset gate, if the first reset gate on the measure qubit is imperfect, then when you do this leakage I swap, you'd actually be swapping 2 state into the data qubit, which would be really bad. So the fact that the performance was stable over time meant that the reset was working and the swap was staying tuned up over that time period, which is all very good. All right. Great. So now I've talked about reset and leakage removal. Now I'm going to come to something that someone asked about earlier, which is this issue of leakage due to the readout process itself. Okay. So now we're going to have to look at just a little bit of math, but there's a joke on the slide, so don't worry. Okay, so dispersive readout in superconducting qubits by this point is old news. Everyone knows how it works. You have a qubit, as shown on the left, capacitively coupled to a resonator, and that causes a dispersive shift. Now let's kind of zoom out a little bit and remember how theoretically we get to the idea that there's a dispersive shift. First, you write this Hamiltonian on the top. You have the charging energy of the qubit, you have the junction energy, you have the resonator's charge and flux energies, and then you have a coupling term that involves the charge of both the qubit and the resonator. Okay, that's pretty normal. Eli just talked about this kind of stuff. Okay, then you make your first bad assumption, which is that the qubit has only 2 levels. Okay, that's not true, but everyone does this. So you say the qubit has 2 levels and you replace all of the charges and fluxes with sigma plus and sigma minus for the qubit, and A dagger for the resonator. And you write something and you feel good about yourself because this looks like a quantum optics textbook. Okay, then you make your second bad assumption and you say that the rotating wave approximation should be pretty good. So you take those two terms on the right and you say, well, I don't like this term sigma plus A dagger because that puts a photon in the qubit and in the resonator, and that doesn't conserve energy, so I don't like it. I'm going to get rid of it. Okay, quantum mechanics does not require that Hamiltonian terms conserve energy, but you do it. Okay, so then you get this nice second to bottom line here, where you have the resonator's energy A dagger A, you have the qubit sigma Z, and then you have the coupling terms. So you have a coupling strength G, and you have terms that take a photon from the qubit and put it in the resonator and vice versa. Then you do something that's actually okay. You do the Schrafer-Wolf thing and you do perturbation theory, and you can show that if the qubit and the resonator are detuned by a lot, so if the detuning delta is sufficiently large compared to the coupling G, then that coupling term looks like the third term in the bottom there, G squared over delta sigma Zn. So what that term is saying is that if you put photons in the resonator, the frequency of the qubit shifts, or if the qubit state changes, the frequency of the resonator changes. That's what that coupling term does physically. Okay, this is all pretty good. The dispersive shift that you get out of this Hamiltonian, this G squared over delta thing, that's actually not bad, and you can make readout work. And the founders of this field, this technology, Andreas Wallraff, Dave Schuster, Alexander Blay, Michel Devereux, they did this and it worked and it's great. And we all use dispersive readout. So this is all true, but it's also lies. And I'm going to show you why, because these first two assumptions here would make you think that there's no leakage, but there's lots of leakage. So now we're going to talk about that. All right, so the fact that there's leakage from readout was actually known for quite a while. There's this plot in the left here from Johnson, that's back in 2012, where they saw that they looked at the fidelity of their readout as a function of the number of photons in the cavity. And what they saw is that the readout fidelity starts to like wiggle around just a little bit. That's the red and the blue as you get to too many photons. But the other thing they looked at was the T1 of the qubit, and that goes nuts. And if you look carefully, you'll see that as you increase the photon number to like just before 1, looks like the T1 goes down, and then you put more photons and it goes back up, and you put more photons up to 10 and it goes down again, and then it goes up again, and then it goes down again and up again and down again. The T1's going crazy. And no one understood what was going on with this. And people made up all kinds of explanations, but none of them were ever validated experimentally, and it's very confusing. When I was a grad student, I was really worried about like what is going on here, and just kind of luckily tried not measuring the qubit's T1, so to speak, but I just looked for the probability that the qubit was in some other state as a function of the number of resonator photons, and that's the plot on the right. So here, there's two kinds of curves. Either we start the qubit in 0 or we start the qubit in 1. So blue, green, red is when you start the qubit in 0, and teal, purple, yellow is starting the qubit in 1. And I've labeled some of the transitions. And so you can see, okay, the teal curve is saying that if you get to like 100 photons, the qubit goes from 1 to 0. Okay, that's a problem. But what really is interesting here is the red and the yellow, which is saying that the qubit is going to the 2 state when you increase the number of photons in the resonator. So you're trying to read out faster, you're driving more power, but the qubit's going to the 2 state. So that was the first evidence that I saw that this thing that Johnson saw was not actually T1, that the qubit is actually doing something somewhat more nefarious. This was really confusing because if you go back to that dispersive Hamiltonian that's reproduced here, there are no terms there that could allow this to happen, right? That's a bit of a tautology because this Hamiltonian neglects the fact that the qubit has a 2 state in the first place. But moreover, there's nothing there that can swap energy between the resonator and the qubit at all. So this was kind of confusing. This was so confusing that I'll never forget, Michel Devereux said that this was the skeleton in the closet of our field, and it remained so for like 10 years. All right, so then finally we did an experiment that kind of shed some light on this. So in the top left there, what we did was we prepared the qubit in the 0, 1, 2, and 3 states and looked at the readout clouds in the IQ plane. and set it up so that they were sufficiently distinguishable that you could actually see what state the qubit was in up to the level 3. Then we did the pulse sequence that's shown in the bottom left there. So we drive the resonator with a variable amount of power, and the idea was to make the bad thing happen, whatever it was. We didn't know what was going on. Then just wait for the resonator to ring down, and then use the resonator with a gentle pulse just to read out what state the qubit is in. So the idea is scramble the heck out of the qubit and then use that readout resonator again to find out what state the qubit's in. And the results are in the top right plot. So the horizontal axis is the drive power, the vertical axis is probability, and the different colors are what state the qubit is in. So we got the same thing that Johnson saw in 2012. In the blue curve, you can see the probability of being in this 0 state goes down and up and down and up, and it goes nuts. But the really interesting thing is that the red and yellow curves, the green and yellow curves are showing that some of that probability is in fact going to the 2 and 3 states, and maybe even higher states. Because when you look at the actual IQ clouds, so you can see in the bottom 3 panels there, I've taken time slices at a few different times that are kind of pointed to there, and looked in the IQ plane, where are the points? And it's just a total mess. If you look at the one on the far right, the qubit is not in the 3 state. The qubit is in like 5, 6, 7, 8, 9, 10, who knows state. It's in the scrambled state. And that purple dashed line in the top plot is the probability of being in a state that we can't even distinguish. And that you can see the probability there goes really high. The qubit's doing something crazy. All right. So we were all very puzzled by this. My theory collaborator, Mustafa Khezri, did simulations and basically came to the conclusion that this absolutely should not happen. Those simulations did use the rotating wave approximation. And so we were thinking, maybe the rotating wave approximation is no good. We're not really sure what's going on. So here's an experiment that really helped us figure it out. Here, what I'm doing is I'm going to drive the resonator to put some energy in it. And due to the AC Stark shift, that's going to change the frequency of the qubit. And then at a variable time, I'm going to pulse the qubit at different frequencies until I get its state to change. So then I know what frequency the qubit was at that time. The color plot on the bottom left is showing the probability that I was able to get the qubit state to flip as a function of time and drive frequency. So that blue line that you see, that's basically showing you the qubit's frequency as a function of time. And you can see, okay, it goes down. That's because the resonator is getting energy. The qubit is AC Stark shifting to a lower frequency. It's kind of doing what it's supposed to. But then at like 30 nanoseconds, the curve just suddenly gets wider. And then at like 70 nanoseconds, just all hell breaks loose and it goes nuts. So we were thinking maybe we're like heating up the sample or something with the readout drive. You know, again, this Hamiltonian doesn't say anything weird should happen. So, okay, let's just double the resonator drive power. That's the plot in the bottom right. And there you can see something very interesting. The curve is steeper because I'm driving the resonator harder and the qubit's AC Stark shift accumulates faster. But the place where it goes nuts, it happens at the same qubit frequency. Doesn't happen at a different, you know, it's not like the time is fixed or something. It seems like it's the frequency of the qubit that's the thing that matters. And that led Mustafa to figure out what was going on, which is illustrated here. Okay, so let's go through this slowly. So based on the fact that that frequency is what mattered, Mustafa was like, okay, this has to be some kind of a resonance effect. So let's consider a transmon capacitively coupled to a resonator. So here I'm bringing back all the transmon levels, and the resonator, of course, has many levels. The transmon is not a 2-level system, so that sigma z is no good. We're going to forget about that. Instead, we're going to draw the full energy level diagram as shown here on the right. So what's going on here? Let's start with the staircase on the bottom. So see the state 0n. So the qubit's in the 0 state, and there are n photons in the resonator. There's another state where you could have the qubit in the 1 state and n-1 photons in the resonator. So that's transferring 1 excitation from the resonator to the qubit, and so forth and so on. And the staircase goes down because the delta between the resonator and qubit, omega resonator minus omega qubit, is positive. So if you're taking photons out of the resonator and putting them in the qubit, you have less overall energy. So you get this staircase. We call that an RWA strip because in the rotating wave approximation, you have to stay within a staircase. There are no terms that can take you out of it. But there are other strips. So the strip above is the one that has 1 more photon. The strip above that has 2 more photons, and so forth and so on. And okay, I just explained the rotating wave approximation. only keeps the Hamiltonian terms that keep you within a strip, so nothing crazy should be able to happen. But the rotating wave approximation is an approximation, and it's not a very good one in this situation. So when you put those terms back in the bottom left in red, I've put the terms that we threw away in the rotating wave approximation. I can now add an excitation to the qubit and resonator simultaneously. So I have arrows now in this forest of levels that can be activated, transitions that can be activated. They don't conserve energy, but as long as the system can find an end state that does, it will use those intermediate virtual states. So what happens is you get a resonance between where you started, qubit in the ground state, resonator with n photons. And in this case, qubit in the 6th level, resonator with n-4 photons. And you get there by using the non-rotating wave approximation terms to jump to a virtual state and then conserve energy at the end of the process. So this is really bad because now the qubit has leaked into the 6th level, and that's leakage, right? You really don't want this to happen. And okay, so we took the data that I showed a few slides ago where we looked at what states the qubit was going to as a function of drive power. And on the plot on the left there, we took theory curves, which are the dashed line, the dashed blue line and the solid red line, fit it to the data, and it fit incredibly well with 0 fit parameters. So we knew that we had figured out what was going on here. That plot is showing you the qubit frequency. So we tune the qubit frequency, and we drive, the vertical axis is showing the number of excitations in the resonator, and the points are where something bad happens, and the lines are the theory. The lines are basically, the theory lines come from just diagonalizing this Hamiltonian and looking for resonances. That's basically it. So we called this measurement-induced state transitions, and I want to really call out my collaborator who's now at Google, Mustafa Khezri, who figured all of this out when he was, I think he might have been a postdoc or a grad student at the time, I don't remember, but it was amazing work by him, and he really cracked this problem open. All right. Now, just to remind you, this process requires that both of the assumptions we made in coming up with the dispersive Hamiltonian be revisited. You need to take into account the fact that the transmon has multiple levels, and you need to get rid of the rotating wave approximation in order to understand this. Yeah, go ahead.
Why is there a resonance n 6 n-4 and not in a avoided process?
So you're absolutely right. When you look in simulation, or if you do numerics, it is an avoided level crossing. So what you do is you diagonalize and you look for crossings. And when you see crossings, that's basically when this missed process is going to happen. You're absolutely right. Yeah. Okay. All right, now there's one more complication. So everything I've shown you so far with those staircases that go downwards like that, that's for the case when the resonator frequency is bigger than the qubit frequency. If the resonator frequency is smaller than the qubit frequency, then you get a situation like the thing that's shown on the right. So this is one RWA strip. So the excitation number here is conserved. But what happens as you take photons out of the resonator and put them in the qubit, at first, is that you have more energy because the qubit's higher frequency. But remember I said before, the transmon has a negative anharmonicity. So eventually, as you keep putting photons in there, you go up by a smaller amount and then eventually start coming back down. So this manifold of states actually bends over, and now you have resonances all over the place because every RWA strip is resonating with itself. You don't even have to get rid of the rotating wave approximation now to have a bad leakage process. And that's described in the paper, the 2023 paper by Mustafa listed there. All right, so putting the readout resonator below the qubit looks like kind of a bad idea. There's a long history of this problem, just to summarize on NIST. There's prehistory where people saw problems with readout and didn't really know what it was. There's the 2016 paper where we identified that it was a resonance process. In 2023, we looked at the case where the resonator is below the qubit frequency. And then there's been this really amazing flurry of theory work, largely from the Sherbrooke group. There's a paper by Cohen in 2023 where they showed that this whole process actually is analogous to the chaos that you get when you drive a pendulum. So a transmon is like a pendulum, it's Hamiltonian. And even in the classical pendulum system, you can see something kind of reminiscent of this mist process, which is kind of cool. And then last year, Marie Dumas published this amazing paper that gives a theoretical framework that ties all of these different cases together and explains how to do the numerics in an efficient way. All right, so now we've talked about leakage leakage removal, and we've talked about leakage coming from readout. Let's talk about the architectural implications. So this is the thing that you need to think about when you design your devices, which is the point of the workshop. Okay, this was supposed to be a click-through slide, but we'll just have to figure it out. Because leakage is such a problem, for a while, many of the results you've seen from Google are designed in the way shown on the left. So here I'm plotting the flux bias on the horizontal axis and the frequency on the vertical axis. As you know, the transmon has an upside down arch in its frequency versus flux. And you like to do gates near the top where it's not too flux sensitive. And we simply just put the readout and resonator below because reset and leakage removal is that important for error correction. The problem with that, as I mentioned, is this thing in the bottom right where the RWA strips bend over and the readout causes all kinds of leakage. So the price we paid for that was really, really slow readout. And you'll see that if you look in our papers for the past couple of years, it's kind of conspicuous that our readout speeds are much slower than some other groups. And the reason really just comes down to the fact that we needed to have leakage removal. So it's kind of a problem. We'd like to speed up readout. It's unclear how to do that. It's funny, I actually just heard some folks in the other room saying, well, what if you just had 2 resonators? You could consider doing that. You could put a reset resonator below, put the readout resonator above. That might be a good idea. You now have 2 lossy resonators connected to your qubit, so you're going to pay a T1 cost, and it's more complicated. Whenever you put more modes on the chip, things go crazy. There's another problem here, which is that we'd really like to reduce the qubit frequency because there are fewer TLSs when you go to lower frequencies. But the problem is if you go too low, there's nowhere to put your reset resonator. Because if its frequency is below like 3 gigahertz, it'll be thermally occupied, even in a pretty good dilution refrigerator. And if the reset resonator is occupied, when you try to do data qubit leakage removal, you'll actually be injecting leakage from the resonator into the qubit, which is awful. So this is an architectural problem that needs to be solved. I think in the next few years, we're going to see a lot of groups confronting this issue. And we'll see what happens. And I think the interesting design work to be done nowadays, there's a lot of interesting design work to be done in tackling this problem head on. There have been proposals for microwave activated resets where you wouldn't necessarily need to put the reset resonator below the qubit. They tend to be kind of slow, but progress there would be really helpful. Other ways of doing readout where maybe you could move the readout resonator really far away so you have less Purcell effect could be interesting. There was a paper from Michelle Devray's group at Yale, Tom Connolly, and Pavel Karolovich recently showed that you can detune the resonator by like many gigahertz and actually readout works pretty well. So yeah, I think this summarizes the design problem that I think my team at Google is going to be tackling for the next couple of years. All right, that's the end, and I think we have time for questions. Yeah, let's do like one audience, one online. Let's start online.
How do we correct the error in the chain undetectable?
Okay, the question is, how do we detect an error chain in the surface code that's undetectable? By definition of undetectable, you can't. If there's an undetectable error, then your computation is going to have failed. And so the whole point of quantum error correction or any error, I mean, even classical error correction, you're trying to not have undetectable errors. I think there was a question here. No? Okay. Yeah. So just to make sure I understand, you want to do the swap or not do the swap? Yeah. Yes. Yes. Yeah. Okay. So the question is, I'm going to repeat it because I'm not sure how well, yeah. The question is, why don't we replace this reset with a measurement, and then we'll have some hope of knowing that there actually was leakage, and the decoder can use that information. That is a good idea. What remains to be seen is how much it actually helps you, because the readout tends to be the worst thing in the system. So once you get to a multiplexed readout, and you have to multiplex because the hardware overhead of readout is so enormous, if you're, I'm going to say like 99% readout fidelity is, maybe we'll get to 99.5 in big systems. I think it's going to be a while before we do better than that. And so then the question is, if you only know to that accuracy that you leaked, how much are you helping the decoder really? And my understanding, I talked about this with collaborators at Google, is that it helps the most if there's a lot of leakage. If the leakage is already pretty low, which it is, it doesn't help you that much. So we haven't been doing it yet. This may turn out to be useful if our readout gets better, if there's a breakthrough in decoding, like how the decoders handle that information, things like that. Yeah. My understanding is right now it's not that important. I could be wrong about that, though. Don't take that as gospel. Was there another online question?
That's not my question. It's from Matt Myers. He asked, how to decide the time for the hold?
How do you decide the time for the hold? I think probably that question refers to this slide. So this is the MLR gate. So the qubit crosses the resonator frequency and then spends some time below the resonator that's marked in red as hold. The reason that that hold is there is so that the energy can leak out of the resonator, because you do not want to pick that energy back up as you cross the resonator to put the qubit back where it needs to be for gates. And if the resonator is occupied when you're trying to do gates, remember that reset resonator was also our readout resonator. So it would be dephasing the qubit. So the hold time is essentially determined by the ring down rate of the resonator.
Yeah, one of the theory papers from the Schipper group showed that you do these nice simulations identifying that there's specific qubit resonator tunings that are like really problematic for you, and you stay away from them. Kind of avoid them.
Yep.
You try that and find.
Yeah. Yeah. Okay. Yes, this is absolutely true. So the question stated that if you look at simulations of this leakage induced by readout, if you have a tunable qubit, there are qubit resonator detunings where the number of photons you need to get leakage increases. There's like better and worse frequencies. So yeah, of course we pick the better frequencies. But again, and this is kind of you could give a whole talk about this. If you're doing a single qubit experiment, you can do whatever you want. When you have something that looks like this, and every qubit now has 4 neighbors, you can't just go parking qubits wherever you feel like it, because you'll have resonances with your neighboring qubits. You can even have resonances you wouldn't expect, where you have like 1 photon from your adjustable coupler and 1 photon from the resonator create 2 excitations in the qubit. It's a mess. It's a frequency crowding problem, which this whole field is really just a frequency crowding problem. So yes, there are better frequencies where the mist isn't as bad. And you have to optimize the whole system, with that being one of many ingredients. You had your hand up for a while, so.
So you mentioned how harsh noise is a problem.
Yes.
And on harmony.
Yeah.
The worst error leakage.
Yeah.
The plutonium is charge insensitive, frequency sensitive, and it has a longer, more stable qubit, but it's also very low frequency. And then you just gave also a bunch of reasons why readout and it becomes problematic at low frequencies. So I was wondering, get your perspective, the trade-off. Like, is this fatal in your opinion, low frequency?
I don't think it's fatal, and this is an absolutely excellent question. Let me go to my DQLR slide. Okay, so the question was this. I just said that you can't put the reset too low because it'll be occupied. But then there's all this research into very low frequency qubits. Like I'm talking like FM radio frequencies, like the fluxonium. So how can those things be true at the same time? The qubit being at a low frequency is okay. because let's say you can initialize it into a ground state somehow. Okay, it's at a low frequency, so its rate to excite from the thermal environment will be bigger than it would have been at a higher frequency, but that's okay. The problem here is if the resonator isn't cold, you're actually injecting leakage. You need to have a cold bath somewhere. It doesn't have to be the qubit. In this case, I didn't say anything about the qubit. The qubit could be getting leaked a lot, but I have a way to get rid of it. So that's the difference. It's okay for the qubit to have an upwards rate from the 0 state to the 1 state, from the 1 state to the 2 state, as long as my rate of pulling that leakage out is fast enough that the surface code decoder is happy. You don't look happy with that answer.
Trying to visualize.
Oh, okay, okay.
I look mad.
Oh, no, okay. I mean, you could literally, this is a real analogy. You could imagine standing out in the California sun with a black t-shirt on, but you've got a cold iced tea. You're getting irradiated, but if you drink enough iced tea, you stay cool. It's exactly the same thing.
That's a great analogy.
Yeah. I hope somebody can like name some reset protocol iced tea with some stupid acronym. That would be awesome. Okay. Go ahead.
Yeah, no, there's online question. If there's a question from Chris Warren, how much do you get for free by moving from dispersive readout to longitudinal readout?
That's hard to answer because I haven't seen Okay, the question was, what do you gain by going from dispersive to longitudinal readout? Longitudinal readout, if it were shown to really work, is really nice because you get your signal to noise ratio faster than in regular dispersive readout, and you don't have as much Purcell effect. So longitudinal readout would be fantastic. It's not an easy circuit to design. Maybe if you stick around in this course, you'll figure out how to design longitudinal readout. That'd be awesome. There's some evidence that longitudinal readout might also have less leakage, but I'll just say that so far that has been a design challenge that has not been solved. I just want to make sure I don't miss anyone who had their hand up for a while. But
Question is about you keeping a readout below.
Mhm. Yeah.
And I'm trying to understand if there is a historic reason why you kept it below it and not it, as seen in many other groups where a readout was needed.
Yeah.
So what was the initial motivation?
Yeah, okay. So the question was, why did we put the readout resonator below the qubit instead of above the qubit? Every other group puts the readout resonator above the qubit. So what were we thinking? Our readout resonators were above the qubits for a long time, but then we had leakage and we had to fix it. So we decided to just do this and put the resonator below the qubit and use it for both readout and reset. The problem here is that the transmon cannot tune upwards away from its insensitive point. If it could, we would just have a single resonator up here above the qubit and use it for both readout and reset, and everything would be great. Another design challenge. But it doesn't tune upwards, so you're stuck.
The answer is you're using a single readout.
Yeah. Mm-hmm. But I mean, we had before we knew that we needed this leakage removal, we only had one resonator and it was above the qubit. Now we only have one resonator and it's below the qubit, but we paid for it in readout speed. Yeah.
My question was very much related. Are there people who are working on multi-level reset analysis where you can use a resonator off? Is it fundamentally, that's just not going to work. Fundamentally, you have to have a resonator.
There's a couple of things that can be said. So there, like I mentioned briefly, there are microwave activated procedures where, roughly speaking, you have a resonator somewhere above the qubit and you drive the system at the right frequency, and that enables a transfer of energy from the qubit to a higher frequency into that resonator. That has been demonstrated in the literature. I believe it's called Foggy, F0G1 reset. I can find you the reference for that if you want. That's a very nice procedure. It's not as fast. This procedure is very fast when you just cross the resonator and dump your energy. The other problem is with things like Foggy, just as a general statement, as soon as you start driving these nonlinear systems hard, you get things that are like mist. just from driving this reset procedure. So you just have to be very careful. Like I said to this other gentleman's question, all of these things are frequency crowding problems, all of them. I think that might.
Time for maybe one more question.
I think we're done. Okay, thank you very much for your time and thank you for inviting me.